Okay. All right, so this is section 5.1. We're going to cover this today, and that should be it. Let's take a look. A random variable is a variable whose values change. They determined by chance. So it depends on it. I hate to say change, but it's determined by chance. If we look at data on this, if we look at data, we have two types of data, and I think we've covered these before: qualitative data and quantitative. Quantitative is numerical, a number. And qualitative, you can put it in some kind of category, like the color of your eyes. You know, the color of your eyes is qualitative, and maybe your age, how old you are, is quantitative. And then when we do quantitative data, there's two types of data that we want to look at, and I think we've looked at these also. Discrete and continuous. Discrete are whole numbers. 5, 1, 2, 3, 4, 5. You can't use decimals in discrete data. They're countable. 1, 2, 3. You can actually count them. Continuous, you can't always count every single number. Continuous, can you tell me all the numbers between 1 and 2? Well, I could do 1.1, 1.2, 1.3, 1.9, 2.0, but you could also do 1.11, 1.12, and then you could do 1.111. Do you see continuous? It uses every single decimal place possible. It goes on forever. You can create tons of continuous numbers because the number of numbers between 1 and 2 is infinite. It just depends on how many decimal places I go. So continuous are using decimals, and it's every decimal place in between the two numbers you're talking about. And I've done this example before. If I was 5'2", and the next day, or 1 year, I measured myself at 5'2". The next year, I measured myself at 5'3". I didn't just overnight jump from 5'2" to 5'3". I went from 5'2", 0.000001 to 5'2", 0.0002. You increase at small decimal places, and it's continuous. These decimal places go on forever if you have an accurate way of measuring it. So as we move down this list, discrete probability consists of values. A random variable can assume and correspond probabilities of value. So we're going to kind of deal, this table down here is called a discrete probability distribution table that we're going to create today. Discrete probability distribution table. So it says, in order to revisit this, let's flip 3 coins. Remember when we flip coins, you could have head, 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 tail, head, tail, head, tail, head, head, tail, tail, head, tail, head, tail, head, tail, 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 tail. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 different possibilities for flipping 2 coins. If you look, there's no other combination you could use. Hopefully I didn't use one twice. I forgot something. So if you look at it, here's a discrete. We're talking about how many of these outcomes are no heads, and there's one of them. 1 out of 8. The probability of getting no heads is, this is the only one that has no heads. Tails, tails, tails. That probability is 1 out of 8. The probability of getting one head, well, this one has only one head in it. This one has one head, and this one has one head. So 3 of the 8 outcomes have one head. And sure enough, if I lower this a little bit, 3 out of the 8 have one head. And 2 heads. Let me change my color. This one has 2 heads, this one has 2 heads, and this one has 2 heads. There are, once again, 3 out of 8 that have 2 heads, and 3 heads. There's only one of those. Maybe I should have used a different color. There's only one of those, and it's 1 out of 8. So no heads, there's 1 out of 8, that's all tails. 3 heads, there's only one of those, all heads. And then we have 1 head, we had 3 of them, and 2 heads, we had 3 of them. So if we take this data and create a corresponding probability distribution table, I'm going to actually show you. Oh, where's, I thought, oh, actually, that's it. This is how I would, yeah, this is actually it here. I mean, this is how I would draw the table. I mean, they did the same thing. No heads is 1 out of 8. The probability of no heads is 1 out of 8. The probability of 1 head is 1. That's a 1. 1 head is 1 out of 3 out of 8. 2 heads was 3 out of 8, and 3 heads is 1 out of 8. If you notice on a probability distribution, so we need to talk about that. If we add up all these down at the bottom, 1/8 plus 3/8 plus 3/8 plus 1/8, if you look at it, it adds up to 8 over 8. 8 over 8 equals 1. When you do a probability distribution table, your probability equals 1. It has to equal 1. It has to add up to 1. If it doesn't add up to 1, it's not a correct probability distribution table. So let's construct a probability distribution table for a single dice. To roll a single dice, the outcomes, you know, and for the 3 coins, the outcomes was no heads, 1 head, 2 head, 3 heads. For rolling a single dice, you can get a 1, a 2, a 3, a 4, a 5, or a 6. These are the outcomes. Does anybody know the probability of rolling a 1 when you roll a single dice?
1 out of 6.
1 out of 6. Same thing as a 2, a 3, a 4, a 5 is 1 out of 6. And if you roll, you know, roll a dice and you get a 6, its probability is 1 out of 6. If you add those up, you get 6 over 6, which equals 1. So this is the probability distribution table for rolling a single dice. That's, I mean, that's the key to this. And this is the question. Actually, this question is on the test and it's in the homework. The key to this is that the probabilities add up to 1. So they add up to 1. They can't add up to more than 1. They can't add to less than 1. The probability distribution table will add up to 1, showing 100% of the data has been reported. I'm going to tossing coins, graphically probability of tossing 3 coins. Oh, well, we already did that. That was the head. So we already did that one. Oh, the graphic probability. So they want to show you that even if you have a probability distribution table, you can graph this. And so in the next pages in the workbook, they graphed it. The probability of getting, the number of heads is 0 heads, remember, was 1 out of 8. 1 head was 3 out of 8. 2 head was 3 out of 8. And then 3 heads, once again, was 1 out of 8. And 1 out of 8, 3 out of 8, 3 out of 8, and 1 out of 8. If you add them up, the probability has to add up to 1. And they show another graphic representation coming up on the next slide. If I can get to it. I thought they did. Where is it? I really thought it was here. Did I miss it? Oh, I guess this is something else. Is that's something else? Okay, I thought there was another way of graphing it. Oh, I guess not. All right, so here's a homework problem. Construct a probability distribution for customers 1, 2, 3, 4, 5 items at a convenience store. And then they give you these numbers, 0.29, 11, 26, 0.16, 0.18. Now, the thing about this is, it's pretty self-explanatory, just in case you get confused. The first one, number 1, is the first probability. That's how we got 0.29 here. The second one, number 2, buying 2 items, is the second. So you have to keep them in order. 0.11, 0.26, and so on and so on, 0.8. Add up these probabilities, 0.29 plus 0.11 plus 0.26 plus 0.16 plus 0.18, except I definitely typed that in wrong. Let's try this again. I'm hoping it adds up to 1. And sure enough, when I add them all up, it equals 1. So that's a good probability distribution table. And here's a graph of it. This is another representation. When we say x is 1, it goes up to 0.29. When x is 2, it goes to 0.11. So they're just going to show you in this next slide. When x is 1, it goes up to 0.29. When x is 2, it goes to 0.11. I mean, it's hard to see. It's past 0.1, so 0.11. And so on and so on. So this is just another table. The x-axis is what x equals, and the y-axis is the probabilities. Once again, the probabilities add up to 1. And since I've been saying that over and over, that the probabilities add up to 1, here's it in writing. This is the symbol for adding, summing up. To add up or sum. It's called a summation. Sum or add. When you add the probabilities, you should get 1. Now, probabilities have to be between, when you do a probability of something, it has to be between 0 and 1. It can be 0 and it can be 1. But when you add up the probabilities, it equals 1. But a number by itself that has a probability, it has to be between 0 and 1. You cannot have negative probabilities. You cannot have probabilities that are equal to more than 1. That's when they say, I do 110%. I can give it 110%. No, you can't. 100% is all of it. So you can't give it more than 1 or 100%. So determine whether each probability distribution is valid or not. So let's look at A. If I add these up, 0.2, 0.6, 0.1, 0.2 and 0.6 is 0.8, plus 0.1 is 0.9, plus 0.3 is 1.2. This is not a good probability. It's a bad probability distribution. Or we can just say it's not a probability distribution because it adds up to more than one. Let's do this B. 1/4 plus 1/8 plus 1/3 plus 1/8 and 1/8. If you add these up, it adds up to 1. So is this a good probability distribution? Yes, because it does add up to 1. If you add these up on your calculator, it does equal 1. 1/4 plus 1/8 plus 3/8 plus 1/8 plus 1/8. It adds up to 1. C, 1/4 plus 1/4 plus 1/4. They add up to 1, so this is good. And finally, the last one. As soon as you see a negative numbers are not allowed for a probability. So this is a bad one. Because you're not allowed to have a negative. No negatives. No negative probabilities are allowed. And this is one of the, very similar to one of the questions you will have on your test. It just says which one of these is a good probability. They give you 4 choices, and I think only one of them is a good probability. You pick the correct one. Probability distribution. And guess what? We are done. That was 5.1.